And the last person, but not least, is Sebastian Krawczuk. He will give us a little bit information about astrography and amateur astronomy. So hopefully it will be some relaxing also presentation at the end of our meeting. And Sebastian Krawczuk is from Lookout Inc. So Florian.
Hello, we'll start with regular mantra. Can you see me? Can you hear me? And can you see my screen?
Yours. We can hear you and see you, but we do not see your presentation. No.
Okay.
Now we can
what about
see
now?
your screen. Yes.
All right. So welcome. We're going to talk about astrophotography and amateur astronomy. And hopefully at the end, we're going to make a connection to education and outreach to fulfill the requirement for this particular session. So first of all, let's square away the egos here. So my name is Sebastian. I am not a scientist, as most of you guys. By day, I'm an engineer in the San Francisco Bay Area in a company, and I'm also a full-time dad. That's my daughter. And I'm also an enthusiast of an amateur astronomy and astrophotography. In this presentation, we're gonna go through, what is out there to see and photograph, right, in space around us from our planet. We're gonna go quite a bit about the pains and gains of the photography techniques and what equipment is there available for us to take amazing photos of the space. And lastly, we're going to make, of course, the connection. How can we, as amateur astronomers, how can we connect with local communities? What outreach opportunities are there, and even citizen science opportunities for us? So let's begin. What's out there to photograph, right? So, typically we have, of course, our sun, our main star. By the way, all these photos that you see here are taken by me from my backyard, where I live. Some of them that are not taken by me, but grabbed from the vast of internet, I'm gonna tag as such. So sun, right? That's one of the largest objects we can observe. The next one, of course, is the moon. It's a fantastic object to observe, as well as when you can see the craters. It gives a lot of wow effects to people that I share my telescope with. Of course, we have planets, so that's Venus, Mars, Saturn, and Jupiter. We can observe the stars, of course, there's plenty of them at our disposal, but honestly, they're boring. The double stars are probably a little bit more interesting. As I can see, there's a interesting, actually quadruple system. The star clusters are way more alluring and way more interesting. We're going to talk about it later. And lastly, of course, comets. This is a comet Neowise that's visited us 2 years ago during COVID time. So that was very interesting and enlightening event. Speaking of stuff beyond our planetary system, we have so-called deep space objects. And as I mentioned earlier, we have star clusters. Also, what to mention, all of these objects that we're going to talk about here, they are part of our galaxy. And I think that's very important thing to say because people don't sometimes get that. So let's begin with the star clusters. We have open clusters like Pleiades. It's a beautiful cluster next to Orion. You can see it's with your naked eye. It's also called the Seven Sisters. It consists of 7 stars. Of course, there's more of them if you use a telescopic tool to look at the targets. And I believe he was using the movie Moana, right, as that guide for to find Maui, right? The question mark. Yeah, that's Pleiades. We have a double cluster in Perseus. That's not my image. I've grabbed it from the internet. I've seen it many times visually. I've never photographed it. It's beautiful. You can see it with a wide view angle eyepiece. It's just 2 open star clusters next to each other. Really immersive experience. And we have things like globular clusters. These are clusters of stars that are bound gravitationally with each other. there are various theories of what they are. What I've read, they speculate that they, of course, bound by a black hole inside. There might be remnants of other galaxy cores that happen to merge with Milky Way. And we actually find those objects, I mean, globular clusters in other galaxies as well. So that's the very common one, Hercules, globular cluster M13. Beautiful, one of the biggest ones and the brightest one. What else do we have? We have nebulae. These are fuzzy clouds of gas and dust in space. Mostly we have, the most common one, emission ones, they ionize by radiation of the nearby stars. These pretty much light on their own, like a neon light, in hydrogen alpha wavelengths. And this is the most common and the most beautiful object, Orion Nebula. You can see it with binoculars. Of course, from not light-polluted environments, we have reflection nebulae. There's a little bit different objects. They don't shine on their own, but they light up by nearby stars. And this is a beautiful object of Trifid Nebula. And lastly, we have a dark nebulae that actually stuff or dust that's blocking the lights. So therefore, they come out as dark regions. And here's a brief example of Horsehead Nebula in Orion as well. Now moving on the nebulae, we have something called planetary nebulae and misnomer. They were called like that by early astronomers. They are, shells of gas of stars that by the end of their life, our sun's going to go through something like this in the future. So, we better move outside of our planetary system, escape from it before that happens. They were named such as a planetary nebula because they look like planets back or for the early astronomers, but they're not. This is a very famous ring nebula. And lastly, we have supernova remnants. They're leftovers for the massive star explosions. Like Crab Nebula is another great example of what is there to see in a photograph. And lastly, of course, we have other nearest galaxies. Perfect example, Andromeda M31 that was shot from my backyard, and Sombrero M104. I've attempted to shoot this object, but I didn't succeed. This has been grabbed from a bus of internet. Very interesting stuff. So how do we photograph these things? Now, of course, we're gonna, doing long exposures because of very dim light coming back to us. We need to counteract the rotation of Earth, right? If we don't do this, then we're gonna end up with straw trails. And we need to counteract, right, the apparent rotation or motion from east to west of heavens above us. Of course, we're going to use a tracking mount, and there are two types of them. Pretty much, there's altitude azimuth mount. They're very simple, easy to set up. Move left and right, up and down. Therefore, they're very great for visual observations, but they're not very great for photography. Because you have to track objects in two axes at the same time, so they're prone to errors, and they suffer for something called field rotation of the image if you happen to image it in long exposures. Better off you are with something called equatorial mount. It's a mount that, I don't know if you see my pointer, but you align this axis with the north celestial pole or southern celestial pole if you live in the southern hemisphere. They're not intuitive to control, but they like I said, they require pole alignment, but they can track objects with no artifacts like field rotation. Like I said, they may be not the best for visual because the telescope may be in very oddball configurations, not enabling you for observation. And what type of equipment do we have there? We can use just telephotic lenses. Refractors are the first tools of choice. They have one big problem. They suffer from chromatic aberration. We alleviate it by different designs. We have achromatics that correct for 2 wavelengths, apochromatics that correct for 3 wavelengths. They're not perfect, but they do a good job. We also use something called ED glass, which is a low dispersion glass that limits or diminishes some of the effects of aberration, but it's not perfect. The great advantage is that they have very good contrast, but at large focal lengths, when we need to image or observe smaller objects, their size grows and therefore their weight, and it's becoming a limiting factor. We can move to reflectors. They use mirrors to focus light. They don't have chromatic aberration, but they have a bunch of other problems like off-axis coma and astigmatism, which we need to correct, and there are various ways to do this. The benefits that they're compact for the long focal lengths. So they pretty much you make the light to bounce off in a compressed tube. But they suffer for a lot of contrast to the fact that they have an obstruction, like a secondary mirror in front of it. So the image is becoming a little bit more blurry. All of this type of telescopes or optical tube assemblies, that's the short for OTA, they require field flatteners if you want to image it. It's not a big problem for visual, but for imaging, where the sensors that we produce on planet Earth, they flat and straight, the focus plane has to be flat as well, and that's a challenge. Any correction. So how do we do this, right? So how do we image? Let's start with planets. This is Jupiter.
I'm sorry. I want to remind you that you have 3 minutes left and 5 minutes of questions. But if you want, you can talk.
Okay, so accelerate.
During the question.
Thank you.
Sure.
Planets are very small, very bright. They're not prone to light pollution. They require a high local, high focal lengths, etc. What we do, they're very affected by something called atmospheric sink. So the solution is something, we call it like imaging. We shoot high frame per second videos, and we estimate the best quality frames, identify and sort them, align and stack them in software. So the way it looks like, right, you see something like this, and you, like I said, you stack this, you pick the best frames from the video stream, and you end up with something like this. That's example from one of my sessions. We can image big objects like lunar. They pretty much the same concept. You shoot a video and you stack it, and therefore you can get really good noise-free. I mean, not say noise-free, but you can diminish the noise, improve your signal-to-noise ratio with stacking, and also aligned and get good recover quite a bit of data through video stacking. Another way of objects, it's of course solar imaging. It's as its own, it's its own game. Requires hydrogen alpha dedicated filters on very small narrow bands below even 1 angstrom. So 1 angstrom is, I think, 10 to minus 10 of meter. So that's a filtering that when the pass through is smaller than the size of atom. I think atom is about 2 or 3 angstroms, right, in average. You can retrofit an old telescope, or you can get a dedicated one. I got a dedicated one, and here's an example of it. And then you get images like this, where you can look on the chromosphere of the sun. Milky Way is another target. You can use existing equipment without spending so much money. We have DSLR mirrorless and whatnot, ultra wide and wide angle lenses, right? You can put on a star tracker and shoot nice images of Milky Way. The next, of course, for the deep sky objects, we need a little bit longer focal lengths. Then we get into something like higher grade mounts, right, with bigger payloads. We also use something called auto guiding. So we put a secondary camera system that, with the software running on a laptop or a PC, is correcting imperfection of tracking of the mount and sending its corrective impulses. They're doing the exposure, right. We also use stacking, so that improves signal-to-noise ratio, which takes a lot of subframes. You can see that with increasing number of subframes, right, the one is just very noisy, right? But if you stack 30 of them, the noise is diminishing and the details of the objects are improving. We also use something image calibration, so we sample the noise of the sensor and we subtract it from each subframe before stacking. We also measure and try to guess the imperfections of the optical systems through something called flat frames. So vignetting, some dust motes on the sensor can be removed that way. And there's a bunch of free software that allows you to do this. And then, of course, you put it all together with auto guiding. Also, we add it's a beneficial for us to use a autofocusing because the temperature changes through the imaging session for hours, right? That's how we image for the whole night. So you need to refocus once in a while. The elements shrink. We use various different filters to fight the light pollution. In monochrome imaging, we have SHL filters. So that's sulfur, hydrogen, and oxygen filter. We also can shoot using color sensors. There are pros and cons. Since a lack of time, I'm going to go into this. But it's great. And here are some examples. I'm using color with light pollution filter. This is a North American nebula. This is a Rosette Nebula. It's just all pseudo colors. You can reassign them to your artistic preference. This is an example of Eagle and Omega. That's how we're shooting it. This is Omega. This is Eagle Nebula. And if you go in, I wonder if you recognize this target. So I will give you a brief second to guess what it is. That's the Philosoph creation, famous image by Space Telescope. We also have some, improvements in the field. Mounts getting better, tolerances are getting better, encoders for precise tracking. We have harmonic drives as a new thing. We have better cameras now and cheaper with cooling that alleviates some of the noise. Back illuminated sensors, adaptive optics even comes in to amateur astronomy. Of course, computing power improves, right? And the footprint decreases of those machines. We have Raspberry Pis now controlling whole telescopes. These are the image acquisition, not necessarily, of course, the stacking that requires heavy machinery. We have 3D printing that allows us to print parts and stuff. AI and machine learning. The post-processing is getting big, noise reduction and star masking. You can even rent a remote observatory time. There are services like this available, and we have an interesting newcomers in consumer robotic telescopes, like say an IV scope, that brings in amateur astronomy and observation to the masses, right? In a small self-contained package. Here's an example of the telescope live data that I recently purchased and processed. This is from the Southern Hemisphere. Look how much stuff is going on here, right? And you can experience it on your own. So what are the citizen science opportunities? If you build an observatory, right, you can join a JUPAS. It's an amateur astronomy project. They gather or grab data from various different amateur astronomers trying to analyze, right, the weather pattern in clouds on Jupiter. It's also used by amateur astronomers to derotate the images of the Jupiter in imaging of the Jupiter's component. Jupiter spins way fast, so during the imaging, you can get a blurry image. You need to derotate Jupiter. There's exoplanet research possibility. Jupiter-sized planets are possible to observe from the ground, amateur gear, and you can send the data for analysis. Also, you can follow up observation after Kepler and TESS missions. There's a website, Planet Hunters. You can sign up and participate in the project. You can also process Hubble Space Telescope data. James Webb and Vera Rubin Observatory data will be available at some point in time. And lastly, the local community outreach. What can we do, right, to share that? You spend so much money on that gear, right, and on your passion and hobby, and how can you share it with the others? So of course you can share it on social media, get some attention there. There are celebrities, but they're always somebody's better than you are. But never give up. We have Astro being Astronomy Picture of the Day by NASA. These are like the most common places where you can look for or publish your images. There are largest projects like gigapixel mosaics of the skies and the Milky Way, whatnot. People travel to different hemispheres, Spain, Chile, whatnot. You can join local astronomy club, of course. NASA Night Sky Networks membership comes with it for free. You can participate in organized start parties. You can support Astronomers Without Borders. It's a group of people who actually travels to developing countries and shares the passion of astronomy with children and local communities over there. You can support the International Dark Sky Association. We need dark skies. We need to fight the light pollution. I can even, like I did many times, probably like 4 times, host International Observe the Moon Night for your local community. And this is what I got from my kids' classroom this October, when I hosted International Observe the Moon Night, and we also observed Jupiter and Saturn. And this is the impact I made on kids' little minds. This is 4th and 5th grade elementary, just to let you know. And I am done.
So thank you so much. So do you have any questions? This question to audience. Ryan said that your presentation was very cool. So
thank you. Yeah, I wish I had way more things to talk about, but I just plowed through like a jet airplane. I'm sorry for that.
Sure.
Where can we find the photos? Yeah, I have my personal ones, right? I post on Instagram. Like I said, Astrobeam, I think it's the greatest place to look for anybody's photos out there. They're amazing works of art out there. How many telescopes do I have? I've got my solar, I've got Schmidt-Cassegrain, and I've got a red cat. So that's 3 photographic lenses, a few. So that would be about a 5 now. I wish I had more. I wish I had my own observatory. I don't see any more.
There is a question. Okay. So you answered for.
Yeah.
For.
I don't see any more.
Okay. So thank you so much